All right, so in this video, we're going to take a look at the recently-ish released free response questions for AP Physics 1 exam. I believe this is Form J. I can't remember exactly, but this is the main one that was released on the AP website. The exam happened about a week ago, probably by the time I actually get this video posted, but this is for the 2026 AP Physics 1 exam. So going through, I've downloaded the document. I'm going to skip over some stuff and jump straight to the questions. Here's question number 1. Yep, there it is, version J. We're going to go through, but I'm going to give you a heads up. I have written what I predict to be a good representation of what the grading rubric will eventually look like for these questions. So we'll go through this as we take a look at it, but I'm going to show you how to solve it. And while this is not the official rubric because the reading hasn't even happened yet, that's still a couple weeks in the future, the rubric is kind of my best guess on how they would actually apportion the points. Will it be perfect? No, but it would be a good representation of that. So if you're a student that took this and you feel that you didn't get the full correct answers, you might be able to use this to get a good idea of exactly where your score would actually be. Okay, jumping in on question number 1. Question number 1, as a reminder, is the mathematical routines question. And usually, for each of the physics exams, it is most likely to be the most mathematically complex part of the exam, particularly for the free response section. One of the things that I'd recommend, if you're watching this instead to prepare for future exams, one thing that I recommend to my students is maybe skip question 1 and go to question 2 first, because question 1 is most likely to have some of the most challenging math on it, and you'd hate to get started into it, you're all excited and psyched out, and then you run into a lot of difficult math and it kind of gets in your head and kind of ruins your feel. So just as a heads up on that. That being said, we are going to see a little bit of complex math in this, and I'm going to walk us through it. What we've got is water exits the nozzle of a fountain at an angle theta naught above the horizontal. At time t equals 0, a droplet of water exits the nozzle and follows the path shown in figure 1. The droplet reaches a maximum height h1 above the nozzle. Please note, one of the things for me when I'm looking at this, I see not only the diagram, and I've got what appears to be a parabolic arc, a projectile motion problem, which is actually most of what this problem is, but I also immediately notice that they have defined that to the right is the positive x-axis and up is the positive y-axis. For my classes, we pretty much always do that, but you don't necessarily have to do that. However, for this one, they have defined which way is the positive axis, so please take that into account. Note, figure is not drawn to scale. At time t equals tf, the droplet returns to the same height from which it exited the nozzle. So we have the thing coming up and coming back down. For any students that are familiar with my class, the things that we do in there, or some of my video lessons, this is me playing catch with my would-be friend. That's effectively the problem that we've got. This is projectile motion on flat level ground, so this is not a cliff problem. So those are things that we could take a look at. Now, this one is a little but compounded, I would say, by having some fluid mechanics in it, which we're going to see is also part of this question. Part A, on the axes shown in figure 2, sketch graphs of the horizontal and vertical components of the velocity of the water droplets as a function of time t from t equals 0 to t equals tf. And we are given 2 graphs. I've actually seen questions very similar to this. In fact, for AP1, I believe it was question number 1 from the, was it the 2017 or 2018 exam? If you go back and take a look, you may have to do some searching for it. But they had one where there was a stunt cyclist that was riding a bicycle down and then went over a ramp and jumped over like a gorge or some buses or something. But the important thing was they actually had a question nearly identical to this, and it was also projectile motion. So that gives me insight into how hopefully they would break down this particular setup. One other thing that I will say, it is common in the math routines question that you're going to have either derive or some complex actual numerical numbers that you'll have to crunch, though my money's more on derive, but they will also probably have you do some graphing or sketching of things, maybe some free body diagrams, that sort of thing, as part of it as well. So that's something to take note of. The total question is worth 10 points. That is pretty much locked into stone, but how much each of the individual parts may fluctuate a little bit depending on how much they're asking you to do. I don't know for certain, but my money would be on 3 points are going to be exemplified in these graphs. It might only be 2, but I really think it's going to be 3. Okay, so in this, when I go in, let's see, I thought I opened the software. Oh, okay, it must have crashed on me. Give me just a moment, I apologize. It should be loading up in just a moment. However, because I would go over to my whiteboard, but I need the digital whiteboard here. Our key things on this are, we want to look at the velocity component in the x direction and in the y direction for a projectile motion. Now we have an initial velocity, total velocity vector that is pointed up and to the right at an angle of theta naught, as we will see in just a moment. Create new file. Great. We've got the following. We are launching the water droplet with an initial velocity v naught at an angle theta naught above the horizontal. Note that that means that we have a v naught x this way. We have a v naught y this way. And I'll go ahead and fill in something that we're going to need a little bit later. We don't necessarily need it for part A, but I know that we'll need it soon. V naught y would be v naught, the total magnitude, times sine of theta naught. And in our x direction, we have v naught x would be v naught times cosine theta naught. We can see that with our right triangle here. Sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. Moving that around, we end up with this. So we're going to come back to those. When we look at our projectile motion, the thing is going to go up and come back down like this. I usually say crashing into the ground, but we've got our values in the x direction and our values in the y direction. We have for our kinematic values, our displacement, our final velocity, our initial velocity, our acceleration, and our time. In the x direction, our acceleration is 0. Our initial velocity would be v naught cosine theta naught. And because we neither speed up nor slow down, our acceleration is 0. That is also our final. Now they have not defined it, but we often usually refer to this as d, the total distance that we end up going. This is delta x, which I could simplify as d. Okay, great. And then time, we don't actually know, at least right offhand. As we covered in class, our air time is usually determined by our values in the y direction. Our delta y, well, this is where it gets a little bit tricky. Our initial y is here at the water fountain, and when we're halfway through, we are at a height here of h1. This is at T1, I think, and then TF is over here. I forget exactly how they denoted it. But halfway through our arc, we end up here at a height of h1, and then back over here, we end up back where we started with a delta y of 0 if we're going that entire length. That's the other thing that gets a little bit tricky with projectile motion. You have to think about what part you're solving for. Our clue that we want to look at this halfway point is that we need to incorporate h1. Oh, I'm getting a little ahead of myself, but I'm going to fill in just a little bit on this. My delta y would therefore be equal to h1. V final for this setup is 0 because we're no longer going up and we're about to go back down. V initial in the y direction is v naught sine theta. And our acceleration is equal to negative g, and our time we do not know. Normally, we would take our information, since we're not given d, we could solve for time in terms of these things, bring it over, and then solve for that, but that's not something that we're asked to do. So make certain that you're not getting too gung-ho and jumping ahead on it. Look for what needs to be done for the problem. The main reason that I've laid this out, I know that we're going to use this here in just a minute, but the big thing that I want to bring up is this. Our acceleration is 0 in the x, and we have a non-zero positive value. Our acceleration in the y is negative g, which is most likely negative 10. Okay, so when I go back over to my graphs here, I have a velocity as a function of time. Please notice that we have 0 here, so we can have positive values and we can have negative values. I note that because they did define this is positive x and this is positive y. So in this case, our x velocity is a positive non-zero value because the thing is moving forward, and we have an acceleration of 0. Well, on a velocity as a function of time graph, we can get the acceleration by looking at our slope. So for our acceleration of 0 in the x direction, we need a slope of 0 for our x. So on this, I'm going to draw this graph real quick. I'm going to sketch it, but we've got the following. I need a non-zero value that is positive, and I need it to have a 0 slope the entire time. Please note on this particular exam, this might change in the future, this said simply sketch the graphs, not sketch and label. If you needed to label, then you would probably need to mark this as v naught cosine theta naught, putting it in terms of things that you've been given. You are not required to do that for this particular question, or at least that is what is implied by the instruction words. pay attention to your instruction words. They have started bolding them, drawing attention to them. If you're my students, I usually bold and underline them to draw extra attention, but this is how they do it on the AP exam. For the y direction, looking at this, I know we start with a positive non-zero value. We'll go to 0 halfway through the motion, but they actually have us graphing all the way to the end. So I have it after we get up here, it stops going up and starts going back down, so I'm going to end up with negative values. The other thing that I can tell is my acceleration is negative g, that's a negative number, so I need a negative constant number, I should say. So for the y direction, I need to start with some positive non-zero value. I need to go to 0 in the middle and then continue going until I hit the negative of my original value. So this would be negative v naught sine theta, and this would be positive v naught sine theta naught. In this case, one of the things to bring up is, first off, our slope of this graph is negative constant value. It should be negative g. We are not given any numbers. That's why we're sketching, not plotting. But we do need a negative slope. This is also very important because it's not uncommon to make some problems where down is the positive direction. It can simplify some calculations. And therefore, we could have started with a negative v naught sine theta naught and gone up instead. But that is not a completely correct answer, because they have defined that up is the positive y direction. These are all subtle things. If you didn't really think about them, that's okay. Part of this video is also for students in the future studying for later exams to be able to look through the details of previous exams. Okay. The other thing that I'll bring up is this, reinforcing our skills. Our velocity as a function of time graph. Not only can we look at the slope in order to get our acceleration, but if we look at the area under the curve, that will give us our displacement, another important skill. So on that, we know that our total displacement in the y going from here back down to here would be 0 because we come back to where we start. So verifying that, I could look here and I can see I have some positive area here. I need an equal but negative area there to make my total displacement 0 in keeping with the period that we are told to graph. That also happens with us going from positive down to negative. How do I know that it is negative? Well, from kinematics, I know that it was going up and now it's going down. And from energy, if you're looking at this at the end of all of our studies, we know from conservation of energy, it's got some kinetic energy here, goes up and comes back down. It would have the same kinetic energy here, but energy doesn't care about direction. So we have the same speeds, but we have different directions. Okay, that's a lot of extra talk with this, but I want to try and add a little bit more. Once again, these videos can be used in the future to study for upcoming exams. On top of that, we set things up for our derive, which is A2. I feel that this first part is most likely worth 3 points. I predict that the first point might be for having a correct graph for the x direction, which is a little bit simpler. Having a positive flat line at a 0 slope for the reasons that we discussed. Point 2, I think, would be for having a straight line with a constant negative slope for the vertical component. In other words, if you had drawn the following, if you had done this instead, you knew that it started as a positive value, but you thought it just went to 0 at the end, that would get the second point because you did correctly identify that we have a negative slope, but you did not go all the way to the final time, which would be back over here, with our displacement being 0 and our velocity going back down. And that's where the last point, I think, would come in. The third point for a line that begins at a positive value and ends at negative of that value. In other words, that it ends up reflecting around the horizontal axis. So you can see here I've got those marked. Technically, I should mark this as V naught cosine theta naught. But since we weren't instructed to straight up label it, I'm not putting it in terms of the things that we're given. For any students that are watching this in preparation for the APC exam, these are great things to review for the APC exam, just expect them to be a little bit tougher. Okay, going back in. We've got derive an expression for the speed of the water exiting the nozzle. Express your final answer in terms of theta naught and H1 and physical constants as appropriate. Here's where this gives you a clue on how to set it up. Look at what you're allowed to answer in terms of H1. Like I said just a minute ago, I had set up that at one point we will be looking in the middle of this because of the H1. That's how I knew to look there, because of the H1. There are several ways to go about this. I prefer looking at this from the kinematics viewpoint. So in this case, we're looking specifically in the y direction. Our delta y is equal to h1. Our final velocity in the y is 0, because it goes up and we're looking at the point where it's at the top. Now the total velocity is not 0 because it is still moving to the right, but our velocity in the y direction is 0. Our initial velocity in the y is v naught sine theta naught, as I showed earlier. Let's see, our acceleration is negative g, and our time we have no idea. Using the rules that we learned in kinematics, time is something that we do not have and do not want. So I would go to my AP equation sheet and I would get the equation that looks like this. V final squared equals V initial squared plus 2a delta x. I believe they write it slightly differently, and they usually have the delta x as x final minus x initial. In my class, we simplify that a little bit, but this is the main equation that you're actually using. V final is 0 squared equals V naught times sine theta naught, quantity squared, plus 2 times negative g times h1. This should get us the first point, as we'll see in just a moment. I'm starting with an equation from the equation sheet, and I'm making at least one physics move, replacing a value or several values with one specific to this problem. Okay, so with this, I end up with, this comes up to negative 2gh1, which I can add over to the other side. I'm going to do this a little bit quicker. Feel free to pause and watch through this if you'd like. But 2gh1 will be equal to v naught squared times sine squared theta naught. Double check the math on that so that you can see how I got that if you're not able to follow along in your mind. But this is 0 equals, I'm distributing the squareds, that basically turns into this. And then we would have all these multiplied out would be negative 2gh1. I add that over to the other side. I want v naught, so I'm going to divide both sides by sine squared. So I end up with 2gh1 divided by sine squared theta naught equals v naught squared. And my last step would be to take a square root to get rid of the squared. I would end up with v naught equals, I guess I'll go ahead and write that out, v naught equals the square root of 2gh1 over sine squared theta naught. This should be the correct answer. On the breakdown on this, I believe that this is worth 2 points for the derive. I don't know exactly how they've broken them up, but my best guess would be something along the lines of this. The first point for a multi-step derivation that begins with an appropriate kinematics equation, or, please note I said for one of the following, you can do it with kinematics the way that I've done here, or you can also do this with energy conservation, also implied by the H1. The difficulty on that is you got to find out, so we've got our total kinetic energy, 1/2 mv squared, and then we would have that equal to 1/2 mv1 squared. Well, when we're at the very top, we have nothing in the y direction, but we do have some kinetic energy from the x direction. I do have, you're welcome to take a look, I'll try and link this as well with the comments down below, but to the actual grading, I have example responses for both kinematics, which we just worked through here, and I also have an example that walks you through what I think it would look like if you did this with energy conservation. The second point, I'm going to go ahead and claim that it is for a correct expression or mathematically equivalent to the correct expression. In other words, this is the one where I think you have to get the right answer to get this point. You can get this first one just by setting the problem up correctly and making at least one physics move, not just moving something over to the other side. That's a math move. Physics move is when you replace delta x, for instance, with h1. That's your actual displacement. That's you bringing in something from the problem itself. In this case, with the kinematics, the way it works out, I end up with sine squared in the denominator. Over here with energy, because it's based off of the x direction for some of my equations, I end up with 1 minus cosine squared. Those are actually the same thing. Remember, you may have learned it in a math class, sine squared plus cosine squared equals 1, so you could subtract that over. 1 minus cosine squared is the same thing as sine squared, so both of these should be perfectly good answers. All right, so that's the first part of the derive. Then they want us to continue. The nozzle has a circular cross-section of radius r0. Derive an expression for the volumetric, the volume flow rate of the water exiting the nozzle. This is one where I believe my lessons actually talk about this at least a little bit, but I haven't focused on it as much. I'm going to try and hit it a little bit harder in the future. But we get this from our lesson on continuity equations. So if you go over to my YouTube channel, which you may already be on, you can check out the video on continuity equation, and I'll double check if this is in there. I forgot to check beforehand. But keeping moving on this, express your final answer in terms of theta naught, H1, and R naught. Basically, note that this is the second part of this. So they're kind of wanting you to use the same thing or use your answer to the previous part. We'll see how that works out. Begin your derivation by writing a fundamental physics principle or an equation from the reference sheet. Now, I think a number of students might have gotten confused on this, especially with the H1, that they might have thought that they needed to use Bernoulli's equation, but Bernoulli's equation isn't going to give you a volumetric flow. In case you didn't catch this in the classes, I know I've talked about it, but only very briefly with my classes thus far. We end up with the following. This is called the continuity equation. A1V1 equals A2V2. This is for flow rates. Basically, my part of the lesson usually involves me talking about covering a garden hose with your thumb. If you make the area smaller, this goes down, and therefore the velocity, the speed has to go up. The water comes out faster. One thing that is I haven't necessarily focused on as much in the past, and I'll start to again, area is meters squared, is the units, and velocity or speed would be in meters per second. When you multiply those out, that gives you meters cubed per second. This is a volumetric volume flow rate, volume per time. In short, when you take the area times the speed, what you get is actually your volume flow rate. So far as I know, this equation is not on the reference sheet. This equation is, but there isn't necessarily something that tells you volume flow rate. So if this is not something that you are familiar with, then I can understand why that would be a little confusing. In this case, we can get our volume as a function of time, or sorry, not a function of time, divided by time, this is our volumetric flow rate, is equal to our area times our velocity. Well, in this case, we've got the area. They told us that it's a circular opening that has, so that's pi r squared, and a radius of r naught, quantity squared. That would be the area of it, and I would multiply that by how fast it's going. Well, that was v naught, which is the same thing as, I could write this out. Oh. Please note my derivation begins with an equation from the equation sheet. Here's my continuity equation. I've identified that my volume per time is equal to this, and therefore I have my volume per time is equal to this. And finally, my last step is my volume per time equals pi r naught squared times the square root of 2g h1 over sine squared theta naught. Now, I think in these two parts, they're worth 4 points total, maybe 5, but I apportion them as about 4 points. I bet one of the points is for getting the correct answer, at least at 1 point. I put it earlier in this spot. It might be that you'd, to get that last, all 4 points, you're going to have to end up with the correct answer partway through. But on this one, what I ended up doing was, I had it for the first two things, setting up and then working with the first derivation, and 1 point for getting the correct answer on that. For the second one, setting up and working with the second part, with the continuity equation as we laid out here. And then for this one, it would be for a correct expression for area in terms of R naught, or for a correct expression or an expression consistent with what you got in this part. In other words, I think this is the hard one to get. And there's a good bet that they've set it up that if you didn't get this, you only missed out on 1 out of the 4 points. They usually set it up that way. So once again, don't think that if you can't do one part of the question that you're sunk or cooked or whatever the appropriate word is now with you kids and your music. But you still can get a lot of partial credit on this. So don't let it get in your head if you can't quite get it to the answer you're looking for. Show us what you know and you can still get partial credit. In this case, I've got this here. I believe that that's the correct answer, and that would set us up for about 7 points. I think on the last few of these that I've seen, when they ask you about the changes, that it's come down to about 3 points, though it might only be 2 points, though I think it's going to be 3. The fountain nozzle is replaced with a new nozzle with a radius smaller than R naught, so we're going to shrink it down. In fact, this is exactly the thumb over the garden hose type thing. The water exits the new nozzle at the same angle theta, so we're keeping the same angle. The volume flow rate of the water exiting the new nozzle is equal. So we got the same amount of water coming through in the same amount of time. This is, once again, exactly the thumb over the garden hose, and we're holding it at the same angle. So now I'm going to increase the velocity that it comes out with, and therefore it would end up going higher and farther, which is where we come to this. A water droplet exiting the new setup reaches a maximum height of H2. Which of the following is the best comparison of that? Indicate this, so by writing one of the following. In this case, H2 should be higher than H1. Justify your answer. In your justification, you must include qualitative reasoning beyond mathematical derivations or expressions. You can use equations in this, but basically when you see the word justify, usually we're grading your words. So if you just have equations, don't expect to get possibly any points at all. Justify is the new explain, for those of you familiar with that old format, but it basically means use your words. In this case, we would say, I would say something along the lines of, our volumetric flow rate, the amount of water in a given time is staying the same, our angle is staying the same, but since I'm making the opening smaller, that means that the water is going to be moving faster at launch. Because the angle stays the same and the water is moving faster, that means that it would, since it's going faster and has a certain amount of it in the y direction, it would take longer for gravity to slow it down to bring it to a stop because it was moving faster. Same gravitational acceleration, but greater velocity would require more time. Because it takes more time to do that, the water would end up going higher. Things along those lines. There are other ways that you could probably get full credit on this, but those are the ones that jump to mind immediately. For me, I'm describing this as, for a selection of H2 is greater than H1, so the correct selection with an attempt at a relevant justification. As I tell my students, relevant means that you're making reference to physics stuff. It doesn't have to be correct, but it does need to be relevant. So you can't say H2 is going to be greater than H1 because the number 2 is greater than the number 1 and therefore it must be bigger. That's not relevant, that's not physics oriented. You can't also say because I like H2 more. I mean, that may be true, but that's not a relevant justification. So on this first one, as long as you've got something that could work on paper, even if it's incorrect, you can get partial credit as long as you're showing your knowledge in there, even if you're not sticking the landing and getting all of it correct. The second point, for a justification that includes that the smaller radius with the same flow rate results in a higher initial speed. In this case, it helps if you identify what changes and what stays the same so that you can solidly predict what the new outcome would be. So identify anything that changes, identify things that stay the same, particularly relevant things. For a justification that includes that a greater initial speed with the same vertical acceleration results in a higher maximum height. This might also be interpreted as for correctly predicting the effect of speed on height. So if you said that H1 would be greater than H2, you might not get some of the earlier points, but if you said it because you concluded that the water would be moving slower, there's a good bet that you could still get this third point. So even though I've written it to say greater speed results in greater height, if you had something where you predicted that it was a lower speed and therefore would be a lower height, you're showing the same knowledge as here, so you might still be able to get that point. Again, this is not the official grading rubric. I'm filming this like a few days after the AP exam posted, or College Board posted this. So this is what I think is most likely to be representative of how the points break down. In another several months, they'll actually release the proper grading rubric. I have example responses on here, but you're welcome to take a look at those whenever you would like. That's a little bit longer than we would have on the actual question, but remember these are going to run a little bit longer because I'm going to explain to you all the things we're doing, and we're also going to talk about the grading rubric as we go through these. So hopefully this video was helpful for you.